In this lecture, we're going to start chapter 28, talking about magnetic fields. Alright, so first of all, let's start with what produces a magnetic field. One way that a magnetic fields are produced is to use moving electrically charged particles, such as a current through a wire, to make an electromagnet. The current produces a magnetic field that is utilizable. So for instance, we've seen electromagnets like this in junkyards or various other places. It's a magnet that can be turned on and off. So you can run current through it and it will create this magnetic field, which you can then use, and then you can turn that magnetic field off to drop something. Now, the other way to produce that magnetic field is by means of elementary particles such as electrons, because these particles have an intrinsic magnetic field around them. The magnetic fields of the electrons in certain materials add together to give a net magnetic field around the material, such as such addition is the reason why a permanent magnet has a permanent magnetic field. Now, we've seen magnets before, simple ones, where you have a north and the south pole, and the arrangements of electrons inside of this magnet is going to determine which pole is positive and which pole is negative. Now, in other materials, the magnetic fields of the electrons cancel out, giving no net magnetic field surrounding the material, just in like a regular material. Okay. The definition of B. So we can define the magnetic field B. So B is going to be the character that we use for magnetic field, or the variable rather. So by firing a charged particle through the point at which is to be defined using various directions and speeds for the particle and determining the force that acts on the particle at that point. All right, so it's going to have some relation between the speed of the particle and the force and charge on that particle. All right, so B is then defined to be a vector quantity that is directed along the zero force axis. So when there's no force, if there would be no force acting on a particle, that's going to be the direction of your magnetic field. And we're going to get into what the magnetic field looks like. It's pretty similar to what an electric field would look like, or how we would draw one. All right, so the magnetic force on the charged particle, FB, so we're going to use F subscript B as the magnetic force, is defined as FB is equal to Q, which is going to be the charge. And this charge can be positive or negative. Right, so you could have a positive or negative force, times the cross product of the velocity of that particle crossed with B, which is the magnetic field. Now here, Q is the charge of the particle again, V is the velocity, B is the magnetic field in the region. This is going to be for like an external magnetic field. So if we send a charged particle through some external magnetic field, let's just say our field, is going this way. And so if this is our B, maybe you have a particle that's going through this magnetic field in that direction with some velocity. Okay, so the magnitude of this force is then just simply going to be Q VB sine of phi, where, this is just the equation for a cross product. All right, so here phi is going to be the angle between your velocity and your magnetic field vector. Okay. So in this case, it would be 90 degrees, right? The velocity and the magnetic field are 90 degrees to each other. Okay. So finding the magnetic force of a particle again. So we're looking at what direction this force is going to be in. All right, so we're going to use the right-hand rule to do this. You should have seen this before in mechanics. So you're going to start by putting your fingers in the direction of the first variable, which is V. All right, so you're going to, as you can see here, you're going to line up your hand with the velocity vector. Then you're going to curl it towards the magnetic field vector. Right, in this case, it's in this direction. So you're going to kind of curl it forward like you did here. And the direction of your thumb is going to be the direction of the force. Right, so in this case, if you have a positive particle, right, because remember it's Q V cross B. Right, if you have a positive particle, the force is going to be in the direction of your thumb. If you have a negative particle, the force is actually going to be opposite the direction of your thumb, because that negative charge is going to put a negative in the equation, right? So the force is actually going to be down in this case. All right, so the force Fb acting on a charged particle moving with a velocity v through a magnetic field B is always perpendicular to V and B. Right, so if V and B, you can call that the x and y plane. The direction of the force is always going to be perpendicular, which is going to be in the z plane. Okay. All right, so the definition of B again. The SI unit for B, or the magnetic field, that follows is going to be the Newton per Coulomb meters per second squared. All right, and we're going to call this a Tesla for short, capital T. All right, so 1 Tesla is going to be 1 Newton divided by Coulomb times meters per second. You can also think of it as a Coulomb per second times meters. So that would be a Newton per current, or an amp times meter. Now, an earlier non-SI unit for the magnetic field is going to be the Gauss, which is a G. So if you see G sometimes, that just is going to be basically 10 to the 4th Gausses is going to be 1 Tesla. All right, so let's look at just some proximate magnetic fields so we have a sense of what the numbers are going to look like. All right, so at the surface of a neutron star, you can have 10 to the 8th Tesla, which is very large. Near a big electromagnet, you only have about 1.5 Tesla, right? So you really need so a Tesla by itself is actually quite a bit of a magnetic field. It's a very large magnetic field. Now, near a small bar magnet, like I showed you before, a small bar magnet is going to be something like this, where you have the north and south pole. You have 10 to the negative 2 Tesla. At the Earth's surface, you have 10 to the negative 4 Tesla. So just here on Earth, the Earth's magnetic field is producing 10 to the negative 4. In interstellar space, pretty far away from everything else, you have 10 to the negative 10 Tesla. And the smallest value in a magnetically shielded room is going to be 10 to the negative 4th Tesla, right? So you always have at least some bit of magnetic field. Okay. Now, magnetic field lines. Again, similar to electric field lines in how they're drawn. So the direction of the tangent to a magnetic field line at any point gives the direction of B, or the magnetic field, at that point. The spacing of the lines represents the magnetic field of B. The magnetic field is stronger where the lines are closer together, and conversely. All right. Okay, so again, similar to how we drew electric field lines, now we have a north and south pole instead of a positive and negative side. And you have the lines kind of going out away from it, kind of going from the North Pole to the South Pole. The closer they are together, the stronger the field is going to be. So right here at the North and South Poles, you're going to have the strongest magnetic field. Right? And then over here, you're going to have magnetic field starts to decrease significantly. All right, just a quick aside over here on the jar here. The magnetic field lines from a bar magnet, again, are shown here. Over in this figure, a cow magnet, which is a bar magnet that is intended to be slipped down into the rumen of a cow to prevent accidentally ingesting bits of scrap iron from reaching the cow's intestines. So the iron filings at its ends reveal the magnetic field lines. All right, so what they would do is they would drop a bar magnet and it would sit inside the rumens or the stomachs of a cow, and it would collect any bits of scrap iron. And you can actually see with one of that was removed, the magnetic field lines. Okay, so just a last note, opposite magnetic poles attract each other, and like magnetic poles repel each other. Again, so similar to our electric charges. If you have like poles, so like a north and a north, it's going to repel. But if you have a north and a south, they're going to attract each other. All right, so let's do an example. A uniform magnetic field, B, with magnitude of 1.2 millitesla, is directed vertically upward through the volume of a laboratory chamber. Right, so it's going from the ground through the ceiling. A proton with kinetic energy of 5.3 mega eV, or electron volts, enters the chamber, moving horizontally from north to south. So this is going horizontally kind of along the floor and through the room. What magnetic deflecting force acts on the proton as it enters the chamber? The proton's mass is 1.67 times 10 to the negative 27th kilograms, and we're going to neglect Earth's magnetic field. All right, so because the proton is charged and moving through a magnetic field, a magnetic force, Fb, can act on it. Because the initial direction of the proton's velocity is not along the magnetic field, Fb is not going to be zero, right? So if the velocity was just going along the magnetic field, there wouldn't be any additional force, right? But since it's not, there's going to be some force involved. Okay, so to find the magnitude of this magnetic force, we're going to use our equation, Fb is equal to q Vb sine phi, provided we first find the proton's speed. Now, of course, since we're given a kinetic energy, we can find what the speed is with k is equal to 1/2 mv squared. All right, so solving this equation for the velocity, we simply get that the velocity is going to be the square root of 2 times the kinetic energy divided by the mass. That's going to be equal to 2 times 5.3 mega eV, and we want to convert this into a unit that we're more familiar with. Basically, we want to get into joules so that all the units are going to work out. So we need to find a conversion factor between joules and mega eV, or if you wanted to convert first to eV, electron volts, and then find a conversion factor to joules. But our straight up conversion is going to be 1.6 times 10 to the negative 13 joules per 1 mega electron volt. Okay, we're going to divide that by the mass, which is 1.67 times 10 to the negative 27 kilograms. Oops, that's a 7. Okay. All right, and then the value that we get for this velocity is going to be 3.2 times 10 to the 7th meters a second. All right, so this particle is moving pretty quickly. Now we want to find what the force, the magnetic force on this particle is. All right, so Fb is going to equal to Q. And we do the absolute value of Q so that we're not introducing a negative sign yet. When we decide which direction it's going in, that's when we'll think about what the sign of the charge is. But we're just going to keep the absolute value for now. So this is going to be Vb sine of phi. All right. And again, you can use theta here if you wanted to use theta. It's just the angle between the two vectors. All right, so now we can go ahead and plug in values. So Fb, our charge, is going to be 1.60 times 10 to the negative 19th coulombs, which is the charge of a, I think it's a proton in this case. Yep, a proton. Then we're going to multiply that by the velocity, which we just found. So that's 3.2 times 10 to the 7th meters a second. Multiply that by our magnetic field, which is 1.2 times 10 to the negative 3 Tesla, as is given in the problem up here. And then sine of 90 degrees. Well, sine of 90 degrees is just going to be 1, right? So we don't really have to worry about this term over here. Okay. The value that we're going to get for this is going to be about 6.1 times 10 to the negative 15 newtons. And again, we're talking about a force here, so it's going to be measured in newtons. All right, if we keep all of our other units correct. All right, so this may seem like a small force, but it acts on a particle of a very small mass, producing a particularly large acceleration. So if we found out what the acceleration was, simply by using F is equal to ma, right, and solving for acceleration, the acceleration is going to be the magnetic force divided by the mass. So that's going to be 6.1 times 10 to the negative 15 newtons divided by 1.67 times 10 to the negative 27 kilograms. So we get 3.7 times 10 to the 12th meters per second squared, right, which is actually a significantly large acceleration. All right, so now we need to figure out what the direction of this force is. So to find the direction of the magnetic force, we're going to use the fact that FB has the direction of the cross product, right? Now, because the charge Q is positive, FB must have the same direction as V cross B, right? We don't have to worry about flipping the direction of the force, which can be determined with the right-hand rule for cross products. All right, so we know that V is directed horizontally from south to north, and B is directed vertically up. All right, so if we look at, so this is, let's say this is the floor of our lab. All right, the velocity vector is going to be from south to north, so it's in this direction. The magnetic field is shown with these dots. All right, so dots are going to represent coming out of the floor. All right, so this is basically coming from the floor to the ceiling. It's coming out of the page to us. If we had something like this, if we use little X's, that means it's going into the floor. Okay, so this is going to be into, and then just dots is going to be out of. All right, so this is coming out of the page, kind of towards us out of the page. Okay, so we know that magnetic field's coming up towards us. So if we do our cross product, we first start with our hands straight up, going in this direction, following the velocity, right? And then we curl our fingers up out of the page, right? So your hand has to be kind of upside down. Facing up, you're curling your fingers up out of the page. You notice that your thumb is pointing to the right. All right, so this is going to be the direction of our magnetic field. Now, if we had a negative sign, if we had a negative charge, like if we had an electron going through, it would be in that direction. Okay. Okay, so crossed fields and the discovery of an electron. All right, so what they're showing here is a modern version of the J.J. Thomson apparatus for measuring the ratio of mass to charge for an electron. This was an experiment done back in the early 1900s or late 1800s. And what he did was he took an electric field, which was established by connecting a battery across the deflecting plate terminals. All right, so you have two deflecting plates here, okay, and you create an electric field between them by just creating this potential between them. It's sort of similar to a capacitor in a way, right? You're creating this this electric potential across two plates. Now, the magnetic field is set up by means of a current system, or by means of a current in a system of coils, not shown. The magnetic field shown is into the plane of the figure as represented by the X's. So remember, as I said before, the X's are going to represent it going into the plane. All right, so you have a magnetic field that's going down into the page, and you have this electric field that's going across the page. Okay? And what that's going to do is provide two different forces on this particle. It's going to give you an electric field force, right? An electric force and a magnetic force. Now, when the two fields in the figure are adjusted so that the two deflecting forces acting on a charged particle cancel. So basically what you do is you take a charged particle from over here and you fire it into these two fields. And then the interaction of these two fields is going to deflect the particle. It's going to end up over here, over here, over here, over here. And then you can actually measure this distance. You can measure this deflection distance. Right? And this will help us develop a relationship between this reflection and what the magnetic field is and what the electric field is. All right, and then ultimately a ratio between the mass and the charge. All right, so getting a little bit ahead of ourselves, let's go and continue. So when the two fields, again, are adjusted, and let's say that they cancel each other out, you can develop a relationship between these two forces. Right? If you know that the forces are going to be equal to each other, we can say that our electric field force is equal to our magnetic field force. We can relate those two equations. So we know that our electric field is just going to be Q times the electric field. Right? The electric field force is just QE. And our magnetic field is Q VB sine 90, right? Because they're going to be perpendicular to each other. Now, just a reminder that these are going to be absolute values, so you don't have to worry about the signs. Okay, and this is actually, since this is just 1, we can get rid of, oops, this is just 1, so we can just get rid of that. All right, now we take this equation, the charges are going to cancel out, and you can relate electric field to your magnetic field, right? So the velocity is actually going to be the electric field divided by the magnetic field. All right, and this is the result that we would expect when the fields cancel out. All right, thus the crossed fields allowed us to measure the speed of the charged particles passing through them. Now the deflection of the charged particle, again, this deflection over here, which we're going to call y, moving through an electric field E between two plates at the far end of the plates, is going to be given by, all right, so this deflection is going to be the charge times the electric field times the length of the plates squared divided by 2 times the mass times the velocity of the particle. Now rearranging this and combining it with our magnetic field, we can find this mass to charge ratio, which is going to be b squared times L squared divided by 2ye. Here, where v is going to be the velocity of, or the particle speed, the velocity of the particle, m is the mass, q is its charge, and L is going to be the length of the plates. Okay, that is it for this lecture. We will pick it up next time.